You hear about magnets and think you know the story. Fridge decorations, compass needles, metal sticking to metal. But underneath that simple attraction sits a quantum trick so strange that when physicists first saw it in 1922, they thought their equipment was broken. Electrons spin without spinning. Metals that should repel each other lock into permanent bonds. And a rule discovered in a Hamburg laboratory changes iron from inert dust into the backbone of civilization. This is not about magnets. This is about the hidden math that turns ordinary atoms into force fields. Instead, two spots. Sharp. Separated. The beam splits clean down the middle. Gerlach sees it first, sends a telegram to Niels Bohr. Quote, "Bohr is right after all." End quote. But Bohr's model is wrong about why. The splitting comes from something nobody predicted, something that does not exist in classical mechanics. Intrinsic angular momentum. Spin one half, two possible states and only two. Spin up, spin down. The Stern-Gerlach experiment demonstrates spatial quantization, published in Zeitschrift für Physik volume 9, page 349 in December 1922. Silver has 47 electrons. 46 cancel out. The 47th sits in a 5s orbital. Zero orbital angular momentum. The split should not happen according to Bohr. Yet the beam divides. Wolfgang Pauli calls it conversion material for even the non-believer Stern. The discovery launches quantum mechanics from theory into experimental fact. Stern wins the Nobel Prize in 1943, not for the silver atom experiment, for measuring the proton's magnetic moment in 1933 using the same technique. That measurement shows the proton is not point-like, it has internal structure. But the silver experiment comes first. It proves electrons carry an intrinsic property that generates magnetic fields without orbital motion. 23 by Bretislav Friedrich, reviewing the centennial of the Stern-Gerlach experiment. And from Physics Libre texts, updated March 26, 2025, covering electron spin quantum mechanics in University Physics Volume 3. These are peer-reviewed publications analyzing the original 1922 Gerlach and Stern papers, including their experimental setup with magnetic field gradients exceeding 10,000 Gauss per centimeter and silver beam velocities calculated from furnace temperatures near 1,000 Kelvin. Now back to the information. The spin projection along any chosen axis takes exactly two values, plus 1/2 or minus 1/2, measured in units of h-bar. Samuel Goudsmit and George Uhlenbeck formalize electron spin in 1925, 3 years after the Stern-Gerlach result. They propose it to explain the anomalous Zeeman effect, where spectral lines split into more components than allowed by orbital angular momentum alone. The spin quantum number ms enters the set of 4 quantum numbers defining every electron state. Principal number n, azimuthal number L, magnetic number ml, and spin ms. Wolfgang Pauli announces his exclusion principle in 1925, published in Zeitschrift für Physik, Volume 31. No two electrons in one atom can share all 4 quantum numbers. If 2 electrons occupy the same orbital meaning identical n, l, and ml values, their spins must oppose, one up, one down. Without this rule, all electrons would collapse into the lowest energy state. Matter would shrink. Chemistry would not exist. The periodic table builds from Pauli's principle. Helium stops at 2 electrons in the 1s orbital, one spin up, one spin down. Lithium's third electron jumps to 2s because 1s is full. The structure follows from quantum mechanics proven by Freeman Dyson and Andrew Leonard in 1967, who showed ordinary matter needs the exclusion principle to remain stable against gravitational collapse. The orbital magnetic moment equals negative GL times. The Bohr magneton times the orbital angular momentum divided by h bar. The orbital G factor, GL, equals exactly 1 derived from classical gyromagnetic ratio arguments extended into quantum mechanics. The Bohr magneton equals E times h bar divided by 2 times electron mass. Numerical value, 9.28 times 10 to the negative 24 joules per Tesla. That sets the scale. Spin contributes a second component. The spin magnetic moment equals negative GS times, Bohr magneton times, spin angular momentum divided by h bar. But the spin G factor does not equal 1. Dirac's relativistic equation predicts GS equals 2. Experiments measure 2.0023. The tiny deviation comes from quantum electrodynamics, virtual photons, the electron interacting with its own electromagnetic field. Calculating this anomalous magnetic moment to 12 decimal places matches experiment and ranks among the most precise confirmations of quantum field theory ever achieved according to Kadada, values published by the National Institute of Standards and Technology. The total magnetic moment combines both terms. For electrons and atoms, the Land G factor links total angular momentum J to the magnetic moment, accounting for the different contributions from L and S. Without a field, thermal motion randomizes the orientations. Net magnetization, 0. Apply a field and the moments partially align, creating weak attraction. Remove the field and thermal disorder returns. Magnetization disappears. Both effects are small. Permeability near 1. Ferromagnetic materials behave differently. Iron, cobalt, nickel, gadolinium. These metals exhibit spontaneous magnetization below a critical temperature even without external fields. The moments align parallel across macroscopic regions called domains, containing 10 to the 12 up to 10 to the 15 atoms, reported in non-destructive evaluation physics references from the American Society for Non-Destructive Testing. Each domain acts as a single magnet. In an unmagnetized sample, domains point in random directions. Total field, 0. Apply an external field and 2 things happen. Domain walls move. Domains aligned with the field grow. Domains opposed shrink. Second, the magnetization direction within each domain rotates toward the field. Both processes amplify the applied field by factors of 100 to 1,000 in iron cores, as measured in solenoid experiments. Remove the external field and many domains stay aligned. Permanent magnetization. This is remanence, the material remembers. Purely quantum. No classical analog. It originates from the Pauli exclusion principle combined with electrostatic repulsion. Consider 2 electrons. If they are indistinguishable fermions, the total wave function must be antisymmetric under particle exchange. The wave function splits into spatial and spin parts. For the total to be antisymmetric, when the spin part is symmetric, meaning parallel spins, the spatial part must be antisymmetric. When the spin part is antisymmetric, meaning opposite spins, the spatial part is symmetric. Antisymmetric spatial wave functions vanish when both electrons occupy the same position. Symmetric spatial wave functions do not. This affects the electron's average separation. For parallel spins with antisymmetric spatial parts, the electrons stay farther apart on average. Lower electrostatic repulsion energy. For opposite spins with symmetric spatial parts, they come closer. Higher repulsion. The energy difference depends on the overlap of the electron wave functions. This is the exchange integral J. When J is positive, parallel alignment lowers the energy. Ferromagnetism. When J is negative, anti-parallel alignment wins. Antiferromagnetism. 1928, titled in translation, On the Theory of Ferromagnetism. He models magnetic systems with the Heisenberg Hamiltonian. Energy equals negative J times the sum over nearest neighbors of the dot product of spin operators. For J greater than 0, the ground state aligns all spins parallel in 2 and 3 dimensions. Temperature dependence of magnetization follows from statistical mechanics. Above a critical temperature, thermal energy overcomes exchange coupling. The material transitions from ferromagnetic to paramagnetic. This critical point is the Curie temperature, named after Pierre Curie, who discovered the phenomenon in 1895. Iron, 770 degrees Celsius. Cobalt, 1,127 degrees Celsius. Nickel, 358 degrees Celsius. Values measured by monitoring magnetization during heating. As the sample crosses the transition, sharp magnetization drop indicates Tc according to thermal analysis methods, documented by TA instruments and application notes from June 2023. The Curie temperature is material specific because exchange coupling strength varies with atomic spacing and electron orbital overlap. Pressure changes interatomic distances. Crystal structure matters. Face-centered cubic iron has different magnetic properties than body-centered cubic iron. Alloying adds complexity. Neodymium iron boron magnets have Curie temperatures around 320 degrees Celsius, making them useful for high-temperature applications. But they demagnetize if heated past that point. Ionic crystals. But iron, cobalt, and nickel are metals. Conduction electrons move freely. Localized picture breaks. Theorists calculate exchange integrals for metallic iron and get wrong signs or magnitudes too small by orders of magnitude compared to experimental Curie temperatures, according to research published in Physical Review B and summarized in Science Direct References on Iron Magnetism, updated April 8, 2005. The problem? Itinerant electrons. Bloch and Stoner develop an alternative framework in the 1930s, treating magnetism from delocalized band electrons. The Stoner model splits the electron bands by spin up band, spin down band. The splitting lowers energy if the exchange parameter, I times the density of states at the Fermi level, exceeds 1. This is the Stoner criterion. When satisfied, spontaneous spin polarization occurs. Ferromagnetism emerges from band structure. Both pictures, Heisenberg localized and Stoner itinerant, capture aspects of real magnetic metals. Modern density functional theory. Calculations published since 2000 combine both using gradient-corrected exchange correlation functionals. The Perdue-Wang GGA functional from 1992 reproduces ground state properties of iron better than earlier local density approximations, as shown by Singh, Lung, Asada, Terakura, and others in calculations from the early 1990s. Still, predicting Curie temperatures from first principles remains difficult. Magnetic phase transitions involve fluctuations and correlations beyond mean field theory. Monte Carlo simulations on Heisenberg lattices and finite temperature density functional methods provide better agreement, but computational cost is high. Iron sits at the center of human civilization. Tools, buildings, weapons, machines. The Bronze Age ends when ironworking spreads after 1200 BCE, but iron's dominance comes from magnetism. Lodestone, naturally magnetized magnetite, Fe 304, guides, compasses. Chinese texts from the 4th century BCE mention magnetic stones. Navigation applications appear in Chinese sources by 1040 to 1044 CE. European adoption follows. Without magnetic compasses, transoceanic exploration stalls. The magnetic properties of iron enable electric motors invented in the 1830s by Michael Faraday and others. Generators, transformers, the electric power grid, modern civilization, all rely on ferromagnetic cores to amplify and control magnetic fields. Iron's Curie temperature sits conveniently above normal operating temperatures, but below melting. The metal stays ferromagnetic during use. Degauss it, remagnetize it. The cycle repeats. The domains reform because the exchange interaction persists below Tc. Heat a permanent magnet past its Curie point, and the magnetization vanishes. Cool it back down, and the domains randomize. No net field. Apply an external field during cooling, and the domains align as they form. Permanent magnet restored. This principle controls data storage. Magnetic tapes, hard drives. Write data by locally heating regions past Curie temperature while applying fields to set bit orientations. Magneto-optical storage like Sony Minidisc uses this exact method. Curie point actuators appear in safety systems. Electromagnets and fast breeder reactors use ferromagnetic materials at their Curie temperature. If the reactor overheats, the magnet loses grip. Control rods drop. Reaction stops. Passive failsafe. Self-regulating soldering irons exploit the same trick. The tip reaches Curie temperature. Magnetization drops. Heating stops. Temperature stabilizes without electronics. Those electrons carry spin information across distances and interact with another localized moment. The coupling oscillates with separation, ferromagnetic at some distances, antiferromagnetic at others, decays as 1 over distance cubed. RkY drives magnetic order in rare earth elements and dilute magnetic semiconductors. Gadolinium becomes ferromagnetic below 293 Kelvin via RkKy, despite having localized F electrons and conduction bands that barely overlap. Magnetic semiconductors doped with transition metals show RkKy-mediated ferromagnetism, investigated for spintronic applications, where electron spin carries information in addition to charge. Devices proposed include spin transistors, spin-based logic gates, and quantum computers using electron or nuclear spins as qubits. Spin Hall effect discovered in 2004 allows electrical control of spin currents. Spin-orbit coupling links electron motion to spin orientation, creating opportunities to manipulate magnetism electrically without applied magnetic fields. The electron's spin magnetic moment interacts with this field. Energy depends on the angle between spin and orbital angular momentum. The coupling constant scales as atomic number to the 4th, power making spin orbit effects strong in heavy elements. Llewellyn Thomas introduces the spin orbit term in 1926. The factor of 1/2 from Thomas precession reconciles the magnitude with experiments. Spin orbit coupling splits atomic energy levels, creating fine structure in spectral lines. For hydrogen, the 2s1/2 and 2p1/2 states have slightly different energies measured in microelectron volts. For heavy atoms, spin orbit splitting reaches electron volts. Lead, bismuth, uranium. In solids, spin orbit coupling generates magnetocrystalline anisotropy. The energy to magnetize a crystal depends on direction. Iron prefers magnetization along the 100 cubic axis. Cobalt prefers 0001 hexagonal. Nickel prefers 111. Rotating the magnetization away from the easy axis requires energy proportional to the anisotropy constant K1. For L10 FePt alloy, K1 equals 6.6 megajoules per cubic meter at room temperature. Enormous. This makes FePt excellent for permanent magnets and ultra-high density magnetic recording. Nanoparticles of FePt maintain stable magnetization in bits smaller than 10 nanometers, critical for pushing storage density past 1 terabit per square inch, achieved in commercial drives by 2010. That field stores energy proportional to the volume. The material reduces this energy by splitting into domains, each domain magnetized in a different direction. The external field shrinks, energy drops, but domain walls cost energy. The wall region spans many atomic layers where spins gradually rotate from one domain's direction to another. The wall thickness balances exchange energy, which favors parallel alignment, and anisotropy energy, which prefers specific directions. Typical domain wall width, 100 nanometers in iron. Moving a domain wall under an applied field changes the magnetization. This is how magnetic recording works. Right head applies a field, wall moves, bit flips. The coercivity measures the field required to flip magnetization. Soft magnetic materials like annealed iron have low coercivity, easy to magnetize and demagnetize. Used in transformer cores where the field alternates at 60 Hz. Hard magnetic materials have high coercivity, difficult to demagnetize, permanent magnets. Neodymium, iron boron, samarium cobalt. Coercivity exceeds 1 million amperes per meter. The hysteresis loop plots magnetization versus applied field. Starting from zero field in a demagnetized sample, increasing field aligns domains until saturation, all domains parallel. Reducing the field to zero leaves remanent magnetization. Reversing the field to the coercive field zeros the magnetization. Further reverse field saturates in the opposite direction. The area inside the hysteresis loop represents energy dissipated per cycle. Transformer cores minimize this loss using soft magnetic materials with narrow loops. Manganese oxide, nickel oxide, copper oxide. The metal ions have unpaired d electrons. They sit too far apart for direct exchange, but oxygen ions bridge them. An electron virtually hops from metal to oxygen, creating a transient high-energy state, then returns. Second-order perturbation theory calculates the effective exchange from these virtual processes. Anderson and Kramers work out the rules in the 1950s. When the metal-oxygen metal angle approaches 180 degrees, superexchange favors antiparallel spins. Antiferromagnetism. Manganese oxide orders antiferromagnetically below 118 Kelvin. Below that temperature, the magnetic susceptibility drops. Sublattices magnetize in opposite directions. Net moment, 0. But neutron diffraction sees the order. Magnetic Bragg peaks appear at positions shifted from nuclear peaks. The antiferromagnetic structure has doubled unit cell compared to the crystal. Temperature, where antiferromagnetic order appears, is the Néel temperature, analogous to Curie temperature but for antiferromagnets. Louis Néel develops the theory in 1936, wins the Nobel Prize in 1970. Neutron scattering becomes the key experimental probe for magnetic structures because neutrons carry spin 1/2 and interact with magnetic moments. Clifford Shull and Bertram Brockhaus share the Nobel Prize in 1994 for developing neutron scattering techniques. Their work maps magnetic structures and materials from simple antiferromagnets to complex helical and frustrated systems. Each site wants to anti-align with neighbors. 3 spins on a triangle cannot all be antiparallel. Some interactions must be violated. The ground state becomes highly degenerate. Entropy remains at 0 temperature. Spin-liquid phases emerge. Kagome lattice, pyrochlor lattice, spin ice. These materials resist long-range magnetic order down to millikelvin temperatures. Dysprosium titanate is spin ice. Below 1 Kelvin, magnetic moments point along local easy axes, creating a pattern obeying ice rules. 2 spins in, 2 spins out at each tetrahedral vertex, exactly analogous to hydrogen positions in water ice. The residual entropy matches Pauling's calculation for ice from 1935. Frustrated magnets host exotic excitations. Magnetic monopoles in spin ice, fractionalized spin-ons in quantum spin liquids. These quasi-particles carry fraction of the original degree of freedom and propagate independently. Experimental signatures include power law-specific heat, broad neutron scattering, and unusual thermal transport. Research continues in materials like Herbert-Smithite and organic salts with triangular or Kagome geometries, seeking definitive evidence for spin-liquid ground states as reviewed in condensed matter physics. Literature from the past decade. Among transition metals with unpaired d electrons, only iron, cobalt, and nickel have the right combination of orbital overlap for positive exchange integrals and sufficient density of states to meet the Stoner criterion. Manganese sits next to iron in the periodic table. 5 d electrons, large spin. But manganese adopts complex antiferromagnetic structures in the pure metal, too much localization. Chromium also antiferromagnetic. Spin density wave. Only certain alloys and compounds of manganese show ferromagnetism. Husler alloys like Cu, 2-methyl, discovered in 1903. These ternary compounds crystallize in specific structures, allowing ferromagnetic exchange between manganese ions despite manganese metal itself not being ferromagnetic. The structure matters. Nearest neighbor distances, coordination, symmetry, all influence exchange pathways. This is why some iron alloys lose magnetism when composition changes. Adding enough chromium and nickel produces austenitic stainless steel, face-centered cubic structure, non-magnetic at room temperature, useful for applications requiring corrosion resistance without magnetic interference. Magnetic resonance imaging, surgical instruments. The stainless steel must not distort the magnetic field. Magnetic recording density increased by 9 orders of magnitude from 1950 to 2000. Early tape drives, thousands of bits per square inch. Modern hard drives, terabits per square inch. Moore's law for storage. The scaling comes from shrinking bit size, but small magnetic particles face a problem: thermal fluctuations. At room temperature, thermal energy kT equals about 25 milli-electron volts. If the magnetic anisotropy energy of a particle drops below 50 kT, thermal fluctuations randomly flip the magnetization. Data loss, superparamagnetic limit. For a spherical particle, anisotropy energy equals K times volume. To maintain stability, kV must exceed 50 kT. As bit size shrinks, volume decreases. Require higher K. This drives the shift from cobalt alloys with K around 10 to the 5th joules per cubic meter to Phi PT'd with K, around 10 to the 7th joules per cubic meter. But high K raises coercivity. Writing becomes difficult, requires higher fields. Write head cannot generate enough field. Solution: heat-assisted magnetic recording. Laser pulse heats the bit past Curie temperature. Moment vanishes. Apply right field. Cool the bit. Magnetization aligns with applied field as the bit drops through TC. Requires materials with engineered Curie temperatures matched to laser power and pulse duration. Demonstrated in labs, commercialized in enterprise drives starting around 2013. The Curie temperature engineering involves adjusting composition, FEPT with added elements. Platinum content controls K and TC. Higher platinum raises both. Fine-tuning the balance enables writing at accessible laser powers while maintaining thermal stability at room temperature. Astronomers use it to map galactic structure. The transition frequency is 1.42 gigahertz, corresponding to wavelength of 21.1 centimeters. The splitting arises because the proton generates a magnetic field at the electron's location. The electron's spin magnetic moment interacts with this field. Energy depends on whether spins are parallel or anti-parallel. The hyperfine splitting for hydrogen equals 5.87 times 10 to the negative 6 electron volts measured to high precision via atomic clocks. Quantum electrodynamics predicts corrections to the hyperfine splitting from vacuum polarization and other radiative effects. Experiments match theory to parts per billion. This validates the fundamental description of spin magnetism. Protons and water molecules, hydrogen nuclei, spin 1/2. Place the body in a strong magnetic field several Tesla. Proton spins precess around the field direction at the Larmor frequency proportional to field strength. For 1.5 Tesla, Larmor frequency equals 64 megahertz. Apply a radio frequency pulse at this frequency. Spins flip. Remove the pulse. Spins relax back, emitting radio frequency signals. Different tissues have different relaxation times. T1, spin lattice relaxation. T2, spin-spin relaxation. Measure the emitted signals. Build an image. Spatial resolution comes from applying magnetic field gradients. Field varies with position. Larmor frequency varies with position. Selective excitation and Fourier transform techniques reconstruct three-dimensional images. MRI becomes standard diagnostic tool in the 1980s. No ionizing radiation, unlike CT scans. High soft tissue contrast. Functional MRI tracks. Blood oxygenation changes linked to neural activity. Brain mapping. Cognitive neuroscience. The physics. Oxygenated hemoglobin is diamagnetic. Deoxygenated hemoglobin is paramagnetic. Local field changes affect proton relaxation times. Bold signal. Blood oxygen level dependent contrast. Discovered by Seiji Ogawa in 1990. Revolutionizes neuroscience by allowing real-time observation of brain activity during tasks. Detailed exchange interaction mechanisms. And from the Kodata values for fundamental constants published by NIST, providing the electron magnetic moment measured to a relative uncertainty of 1.8 times 10 to the minus 13, which is negative 1.00115 9652 18046 Bohr magnetons. These measurements come from one-electron quantum cyclotron experiments and quantum non-demolition. Spectroscopy, as documented in peer-reviewed physics literature. Now back to the information. Other edge, excess spin down, no net charge current in the transverse direction. Pure spin current. This enables electrical injection of spin into materials without using ferromagnetic contacts. Applications in spintronics, where both electron charge and spin carry information. Giant magnetoresistance discovered in 1988 by Albert Fert and Peter Grunberg independently. Nobel Prize in 2007. Layered structures, ferromagnet, non-magnetic metal, ferromagnet. Electrical resistance depends on relative magnetization of the two ferromagnetic layers. Parallel, low resistance. Antiparallel, high resistance. Resistance change reaches tens of percent at room temperature, much larger than anisotropic magnetoresistance in single ferromagnets. GMR enables reading smaller magnetic bits, higher storage density. Commercial hard drives incorporate GMR read heads starting in 1997. Areal density jumps, the physics, spin-dependent scattering. Electrons with spin parallel to magnetization pass through ferromagnetic layers easily. Electrons with antiparallel spin scatter strongly. When the two ferromagnetic layers align parallel, one spin channel conducts well, low resistance. When antiparallel, both spin channels scatter, high resistance. Quantum mechanics determines scattering rates. Majority and minority spin bands in ferromagnets have different densities of states, different Fermi surfaces. Scattering probability differs. For parallel magnetizations, spin-up electrons on the left tunnel into spin-up states on the right, high tunnel current. For antiparallel magnetizations, spin-up on the left, faces spin down on the right, lower density of available states, lower tunnel current. TMR reaches hundreds of percent at room temperature and magnesium oxide barriers, with iron electrodes as demonstrated in 2004. Magnetic tunnel junctions become the basis for magnetic random access memory. MRAM, non-volatile, fast, low power, commercialized starting in the 2010s for embedded memory in microcontrollers. Spin transfer torque allows writing without magnetic fields. Pass current through a magnetic tunnel junction. The current carries spin angular momentum. Spin polarized electrons from the fixed layer transfer angular momentum to the free layer. Torque A on the magnetization. If current exceeds a threshold, the magnetization switches. Right operation accomplished electrically. No need for external field coils. Enables higher density and lower power. ST-TMRAM competes with flash memory for some applications. Research continues on reducing switching current and increasing speed. Characterized by a topological charge, counting how many times the magnetization wraps around the unit sphere. Discovered in chiral magnets like manganese silicon in 2009 via neutron scattering and real space imaging. Skyrmion lattices form below critical temperature, stabilized by Dyalushinsky-Moria interaction. This interaction favors canted spin arrangements. Arises from spin-orbit coupling in materials lacking inversion symmetry. The energy term is proportional to the vector cross product of neighboring spins, unlike Heisenberg exchange, which is a scalar dot product. DM interaction favors spirals and twists. Skyrmions have nanometer size, can be moved by small current densities, proposed for racetrack memory where skyrmions propagate along magnetic nanowires controlled by current pulses. Higher density than domain wall devices, lower power. Topological protection prevents skyrmions from unwinding as they move past defects. The topological charge must change, which requires overcoming an energy barrier. Makes skyrmions robust. Experimental demonstrations show controlled creation, motion, and deletion of individual skyrmions at room temperature in multi-layer thin films reported in Nature Physics and Science journals from 2015 onward. Isolating qubits from noise. Achieving 2-qubit gates with high fidelity. Loss-DiVincenzo quantum dot architecture places single electrons in quantum dots. Dots formed by electrostatic gates on semiconductor heterostructures. Gas, algas, silicon, germanium. Gate voltages control the number of electrons and the tunnel coupling between dots. Exchange interaction, J tunable by gate voltage. J gate turns on, spins interact, 2-qubit gate. J gate turns off, spins isolated. Single qubit operations use electron spin resonance or electric dipole spin resonance via spin-orbit coupling. Demonstrations achieve 1-qubit gate fidelities above 99% and 2-qubit fidelities above 90% in silicon, as reported in Nature, volume 580 pages, 359 to 363, published April 11, 2020. Scaling to many qubits requires precise control and error correction. Surface codes, topological qubits. Research programs aim for fault-tolerant quantum computation within a decade. Nuclear spin acts as quantum memory. Storage times exceed seconds. Hybrid electron-nuclear spin qubits combine both. Demonstrated in nitrogen vacancy centers in diamond. The nitrogen vacancy defect has an electronic spin triplet ground state. Optical initialization and readout. Microwave control. Surrounding carbon-13 nuclei provide nuclear spin qubits. Room temperature operation. Entanglement between electron and multiple nuclear spins achieved. Quantum error correction codes demonstrated on small registers. Applications include quantum sensing. Nitrogen vacancy magnetometry detects magnetic fields with nanometer spatial resolution and picotesla sensitivity. Map magnetic fields from single neurons. Image magnetic skyrmions. Detect nuclear magnetic resonance from nanoscale volumes. The spin Hamiltonian includes electronic Zeeman, zero field splitting, hyperfine coupling, and nuclear Zeeman terms. Understanding and controlling this Hamiltonian enables coherent quantum operations, reported in foundational papers in Physical Review, X, and Nature Photonics from the past 5 years. Combining special relativity with quantum mechanics, Dirac derives the equation in 1928, a 4-component wave function. 2 components for electron, 2 for positron. Spin appears naturally. The solutions have intrinsic angular momentum 1/2. Magnetic moment with G factor approximately 2. Dirac predicts the positron before its experimental discovery by Carl Anderson in 1932. Cloud chamber tracks showing positive electron. Antimatter. The Dirac equation unifies quantum mechanics and relativity. Explains fine structure. Spin-orbit coupling. The negative energy solutions, initially problematic, interpreted as filled Dirac sea. Holes in the sea are positrons. Modern field theory resolves this with second quantization. Electron and positron are particle and antiparticle excitations of the electron field. The spin statistics theorem proven by Wolfgang Pauli in 1940 connects spin to statistics. Half-integer spin particles are fermions. Integer spin particles are bosons. This follows from requiring the S matrix to be Lorentz, invariant, and unitary. Deep connection between symmetry and quantum behavior. The anomalous magnetic moment, difference between measured G factor and the Dirac value of 2, currently measured as 1.1596 5218076 times 10 to the negative 3. Theory calculates this from Feynman diagrams. One-loop diagrams give the Schwinger term from 1948. Alpha over 2 pi, where alpha is the fine structure constant. Higher order diagrams add corrections. 4-loop calculations completed. Numerical evaluation matches experiment. Discrepancy less than experimental uncertainty. The electron G factor is the most accurately verified prediction in all of physics according to tests performed at Harvard and University of Washington, using Penning traps to measure cyclotron and spin precession frequencies of single-trapped electrons. The agreement between theory and experiment validates quantum electrodynamics at the subparts per trillion level. Any deviation would signal new physics, extensions to the standard model, extra dimensions, compositeness of the electron. Searches continue with improved experiments aiming for even higher precision. Otto Stern expects refutation of quantum theory, gets confirmation. The magnetic moment of the atom cannot point in any direction. Quantization, discrete states, no continuous distribution. Isidore Rabi says the experiment convinced him once and for all that quantum phenomena required a completely new orientation. The words are from Quanta magazine, January 4, 2024, reviewing the centennial of the Stern-Gerlach discovery and its philosophical implications. The new orientation is quantum mechanics, probability amplitudes, superposition, measurement collapse. From that split beam flows the periodic table, chemical bonds, electrical conductivity, magnetism, semiconductor technology, transistors, integrated circuits, lasers, all rest on quantum principles, first made concrete when 2 spots appeared on a detector screen instead of 1 smear. Spin is not rotation. The electron does not physically turn, but it carries angular momentum and generates magnetic fields. The math works, the experiments agree, the technology delivers. Form standing waves inside the circle, visible in STM images as ripples. The iron atoms carry magnetic moments. They couple via arc KKY through the copper surface electrons. The coupling oscillates with spacing. Engineers tune the magnetism by choosing atom positions. Single atom spintronics. Later experiments flip individual spins using spin polarized currents from the STM tip. Read and write magnetic information at the atomic scale. Ultimate limit of magnetic storage density. Research published in Science, volume 262, page 218 in October 1993, showing the quantum chorale and follow-up work in the 2010s, demonstrating spin control confirmed the quantum mechanical origin of magnetism from Heisenberg's exchange interaction mediated by conduction electrons, exactly as predicted in 1928. Pauli exclusion, exchange, domains, Curie temperature, 5 quantum tricks turning iron into magnets. The electron carries 1/2 h-bar of angular momentum. Intrinsic, unchangeable. 2 electrons in the same orbital must have opposite spins or violate the exclusion principle. Matter stays stable. When spins align parallel, exchange interaction lowers the energy via Pauli principle and Coulomb repulsion. Ferromagnetism emerges. Domains form to minimize magnetostatic energy. Domain walls separate regions. External fields move walls. Magnetization changes. Heat above the Curie temperature and thermal energy overcomes exchange coupling. Ferromagnetism disappears. Cool back down and it returns. Reversible phase transition. These 5 mechanisms explain every magnetic technology. Hard drives storing data, electric motors turning shafts, MRI scanners imaging tissue, Quantum computers processing information, all trace back to Frankfurt, 1922, silver atoms, 2 spots, spin quantization. No interpretation changes the split beam. The data stands. Experiments reported in Zeitschrift für Physik, Volume 9, 1922, pages 349 to 352 by Walter Gerlach and Otto Stern, titled, in translation, "The experimental proof of space quantization in a magnetic field remain unrebutted. Repetitions confirm. Extensions to other elements validate. Hydrogen, lithium, sodium. Every atom with unpaired electrons shows the splitting. The prediction holds across the periodic table. From that single experiment in post-war Germany using donated equipment and dwindling funds, quantum mechanics transitions from mathematical formalism to experimentally verified framework. The implications cascade through the 20th century. Nuclear magnetic resonance, atomic clocks, masers and lasers, semiconductor physics, superconductivity, all require quantum spin. The splitting comes from the electron's magnetic moment interacting with the proton's magnetic field at the nucleus. The frequency depends on fundamental constants: Bohr magneton, nuclear magneton, hyperfine coupling constant. Measure the frequency. Extract the constants. Compare to independent measurements. Agreement, consistency. The quantum mechanical description of spin magnetism produces testable quantitative predictions, verified to parts, per million. Radio astronomers map the galaxy using the 21 centimeter line. Neutral hydrogen emits at this frequency. Velocity shifts reveal galactic rotation, spiral arm structure, dark matter distribution. Cosmology and quantum mechanics connect through a single spectral line arising from electron spin discovered in a Hamburg laboratory in 1922.